NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hey, good evening, ladies and gentlemen. How's everyone tonight? Good. I'm well, thanks. Well, thanks for everybody for coming out. We really appreciate you coming out to visit us. So here we go. Scheduled to launch in 2018, the James Webb Space Telescope, or JWST, will revolutionize our study of the cosmos. Built to address the questions asked by the Hubble and Spitzer Space Telescopes, but out of their reach, JWST will look deeper than either of those telescopes at infrared wavelengths with a suite of instruments that have capabilities that were not previously available. Tonight's talk will describe JWST as a whole, but will focus on the mid-infrared instrument, or Miri, one of the 4 instruments attached to JWST, which was built as a partnership between JPL and a consortium of European astronomical institutes. Tonight's guest is the JPL project scientist for Miri, and it's his responsibility to ensure that the JPL contributions to Miri will enable it to perform the observations desired by the astronomical community. He received his bachelor's degree in physics from MIT in 1986, followed by a PhD in astronomy from the University of Hawaii at Manoa in 1992. He came to JPL after graduation as a National Research Council postdoctoral fellow and joined the JPL staff in 1994. He's been involved in building infrared astronomical instruments since he was an undergraduate and has specialized in understanding the design and operation of the detectors in these instruments. Ground-based instruments he has worked on have been used on the Keck telescopes, the Palomar 200-inch telescope, and the 3-meter NASA Infrared Telescope facility. He is also a member of the science team and is a detector specialist for the WISE All-Sky Survey, where he had the distinction of having the first scientific paper published using results from that mission. His scientific interests focus on the early stages of the formation of stars, but he has also been involved in a broad range of research topics, from asteroid studies to infrared bright galaxies. Ladies and gentlemen, please help me welcome tonight's guest, Dr. Michael Ressler.
Thanks, Mark. Good evening, and thank you all for coming. This is great, and I'm pleased to talk a little bit about the James Webb Space Telescope, which is NASA's next flagship space observatory. The Hubble Space Telescope is an amazing instrument. It's had an immense impact on how we understand our universe. It's taken images of things from galaxies at the far edge of our universe right down to Mars and everything in between. Its images, inspire us, they amaze us, and occasionally they even amuse us. So the universe is smiling back at you. But this image is actually very scientifically important, as well as being a neat little smiley face. These yellowish galaxies are relatively nearby galaxies, and they're mature. They have sort of normal stars like we'd see in our sky right now, things that are millions to billions of years old, and so they're very mature galaxies. The gravity from these galaxies acts as a lens so that other galaxies behind them are actually focused by the gravity from these older galaxies. Why this is important is these streaks that make up our smiley face are very young galaxies that we see much farther back in time. They started to form closer to the beginning of the universe, near the Big Bang. And so these brightish blue streaks are where the stars are being formed in these galaxies. Part of the reason this is so important is the gravity lens makes them appear brighter than they would otherwise, which means that with our telescopes, they're easier for us to see. And until this spring, in fact, the farthest galaxies that we knew about were all these gravitationally lensed galaxies. This was the only way we could see them. Then in March, it was announced, I should back up. One of the things that Hubble has done is taken a number of deep fields. These are regions of sky that we thought were pretty blank, but Hubble pointed at them for many, many hours, took many hours of exposures, And when we look at them, we see fields that look like this. Almost everything in this image is a galaxy, except for that one star sitting right there. Everything else is a galaxy. When we looked carefully at this image, there is a little speck that when you zoom it in, looks like a blob, and my wife would say everything I look at is a fuzzy blob, but it's this little galaxy that turns out to have formed about 300 million years after the Big Bang. It's very, very far away. It happens to be very bright. It's intrinsically bright, and so we could detect it with Hubble. Most of the others, we have to rely on the universe lensing it for us, using other galaxies as telescopes to help us see these things. But these are some of the breakthroughs that Hubble has helped us make when we're trying to understand the far universe. This is actually one of my favorite pictures that Hubble has taken. This is a planetary nebula. This is a nearby star within our own galaxy that's at the end of nearing the end of its life. Stars, as they age, if they're massive enough, if they're big enough, start to blow off their outer layers. Stars are kind of like onions, they have layers. But at the end phases, they become a little unstable and they start, the energy from the star starts pushing those outer layers away. Occasionally, if there's two stars in here, so the old dying star and another star that's orbiting with it, it can shape the planetary nebulae, and it produces these beautiful structures. This is called the twin jet nebula, because it looks like it has jets of material shooting away both directions. And one of the things I like about this image, not only because it's pretty, it has lots of neat colors, but if you look carefully, you'll notice there are some bright spots in here on both sides. I think what's going on, and I haven't talked to the scientists that have done these observations, but what they think is going on is that there's a lot of material near that star, a lot of dust and material that blew off from the star that's condensing, but it's kind of patchy, like clouds in the sky. And so if you go out some night where it's partly cloudy and see the sunset, there are rays of sunlight that burst through little patches in the clouds. Well, I think that's what's going on here. So there's starlight that's escaping through those little patches and then lighting up the walls with a little more starlight than other places are getting. And then just the overall structure, the fact that you see all this fine detail, it's really a spectacular image. And I do think it's very pretty. So Hubble has done, this is the amazing and inspiring part. To talk about a successor to Hubble, I actually have to talk a little bit about another space telescope. This is the Spitzer Space Telescope that was launched in 2003, and that was actually a mission managed here at JPL. Spitzer also looked at some of those deep fields that Hubble looked at, and this is one of them, not the same one I showed you before, but it's another one. Every one of these little red dots in here is a galaxy that Spitzer detected. Again, that's very far away, very young in terms of the age of the universe. And what they found is there are far more of these galaxies than we had expected. To have this many galaxies within a few hundred million years of the Big Bang implies that the process of forming galaxies happens very early. We might have expected that you'd form a few stars first, and then more stars would form, and eventually there would be enough of them that the gravity between the stars would start making galaxies. But this implies that that one at a time sort of thing isn't the way it works. Somehow we form galaxies and stars almost at the same time, very early on. Some people know what images with infrared cameras look like, and they're not often very good. So people wonder, well, can an infrared telescope take pretty pictures? Well, the answer is yes. This is an image from the Spitzer Space Telescope of a star-forming region. You see a lot of young stars in a cluster here near the most. There's a lot of material right here that form stars, and it's just a very, very impressive picture. So yes, infrared telescopes can take pretty pictures too. Well, looking at the results of Spitzer and of Hubble, astronomers actually 20 years ago already started asking, what do we do after Hubble? What science questions do we think will still be out there that we need something even more than Hubble can help us understand? And so over the years, scientists collected results that they were obtaining and said, okay, well, here's some of the open questions. And so there were 4 science themes, 4 science goals that were set, before the people designing the Webb Space Telescope, and said, here's what we want to be able to do, and here's what they are. We want to discover and confirm the first light-emitting objects in the universe. So right after the Big Bang, stars had to start forming somehow. How did that happen? We'd like to see what those stars look like, what their properties are. Next, we'd like to understand how those early galaxies formed. If they didn't form from, pulling stars together, just how did that process work? In that Spitzer image that I showed you, a lot of those galaxies aren't the big things that we see nearby us today. They're these little clumps of stars, maybe hundreds of thousands of stars forming that little galaxy. And so they had to merge somehow. How did that work? We'd like to look at the earliest steps of the birth of stars, even in our own galaxy. We'll talk about why you need infrared telescopes to study star formation, but we want more information on how they work. We want to see the stars that are 1,000 years old to 10,000 years old. What we typically see now is in the hundreds of thousands of years range. And then finally, planets form around stars. Thanks to the Kepler telescope, we now know of thousands of planets that orbit stars in those particular patches of sky. We'd like to know more about those planets. What can we say about how the planets evolved? And ultimately, if we're lucky, do they have conditions that would support life? So these are some of the things that we'd like the Webb telescope to help us address. And this is the concept they came up with. I'll just point out a couple of things before we move along. All telescopes have a primary mirror. All large telescopes have a primary mirror that collects the light. So light comes in from your object, it reflects off that primary mirror, bounces off a small secondary mirror that relays the light back through a hole in the primary mirror. And then there are scientific instruments that sit behind the mirror that either collect it as images or break it into spectra where we can study what the composition of the sources are. There's a big tennis court-sized sun shield. That's that diamond-shaped structure. This protects the telescope from sunlight and earth light because both of them are bad for our scientific observations. And then not visible underneath is a spacecraft bus that has the propulsion systems and all that sort of stuff. The difference between Webb and Hubble is primarily size, but there are a few more details. That primary mirror of Hubble, the light collecting mirror up here, is about 2.4 meters in diameter, roughly 8 feet in diameter. If you draw a circle around the primary mirror of the James Webb Space Telescope, it's about 6.5 meters in diameter. That's cheating a little bit because part of the mirror is missing. So on average, it's about a 6-meter mirror, and that's a lot easier to say. But you'll notice there are 18 hexagonal segments that make up the primary mirror. So not only does each individual mirror have to be very precisely shaped, we have to be able to get all 18 mirrors to work together as one large mirror. You'll also notice that the Hubble Space Telescope has a shield that baffles it against stray light, whereas Webb is wide open. So if there's any sources off to the side that are shining into the telescope, we will see them. So while Webb is bigger than Hubble, it's not a replacement. Early on, we heard people talking about, oh, there's a replacement for Hubble. Well, not really. Webb is designed to complement and extend with what both Hubble and Spitzer have been able to do. And the key feature of Webb, in order to do that, is it has to work at infrared wavelengths. So I'm going to explain a little bit about what the infrared is, why it's important, why it's really neat, why I do it. If we shine, I should have waited. If we shine a white light through a prism, we get the rainbow thing. We've all seen that. You've seen rainbows in the sky. It's the same principle. It's very natural to ask, well, what's over here? What's past the violet? We also might ask, well, what's over here? What's below the red? William Herschel in 1800 did an experiment where he was trying to measure the temperature of the colors of light. He thought that maybe individual colors might have a different temperature. It was a good experiment to try to do. So what he did is he put a thermometer over here and another thermometer over here as his controls. and then moved the thermometer through the different colors of light. Well, what he noticed was that the purple light was coldest and the red light was warmest. So he did what a good scientist would do and said, well, gee, if it's warmest here, what if I move off just to the side a little bit? I should see the temperature drop, right? Well, it turned out that dark space below the red was the warmest of all, and that's the discovery of infrared radiation or infrared light. And that was the first time we actually discovered energy that, light energy that we couldn't see with our eyes. So it was a huge thing, and it took a long time to develop instruments that would work in the infrared, but it came along eventually. What can we do with infrared light? Well, we can take pictures of meerkats. I'm not sure where this visible wavelength picture was taken, but this is what meerkats look like in the thermal infrared, and I think this is a lot of fun. You can actually learn a lot about meerkats based on an infrared image of the meerkats, because you notice the eyes are bright. Your eyes are deep in your head. They're surrounded by very warm tissue, and so they're going to be warmer than average. Their noses, on the other hand, are dark. Your nose sticks out a little bit, and so it cools off a little bit more, and then there's not as much blood supply in your nose, so it actually looks a little bit cooler. Actually, if you go over to the von Karman Museum just next door, there's a thermal infrared camera there, and you can see what your own face looks like, and it won't look like a meerkat, but it will have some of the same features. You also notice that their toes are cold because they're on the rocks that don't generate heat on their own, and so maybe we don't learn a lot about meerkats in the infrared, but we see some of the things. The gaps in fur are brighter because you can see down closer to their skin, and so that's why their fur looks so funny. Well, there are more important uses for infrared, and one of them is firefighting. If you're in a room full of smoke, it's hard to see anything. But infrared wavelengths, or smoke, is actually relatively transparent to infrared wavelengths. So if we look at this scene with an infrared camera, we see there's a person on the floor that needs to be rescued. And so same sort of thing, he's got a bright face because there's a lot of blood in your face, the clothing is a little bit cooler. I thought it was cool, the oxygen tank on the back of the firefighter is relatively cold compared to everything else, and so it's very dark. So this demonstrates a couple of things that we can take advantage of in the infrared. We can see the temperatures of things, we can see warm and cold, and we can also see through smoke. Well, we can use those same things in astronomy to help us understand the universe around us. This is a little cloud of gas and dust that's zipping around in our own galaxy. It's fairly close to us. All the stars you see here are farther away than the cloud, so there should just be a carpet of stars all over this. But because the dust in the cloud absorbs visible wavelength light the same way that smoke absorbs light, we can't see through the cloud. But if we get an infrared camera and take another image of that cloud, we can see those stars through it. So it turns out there's not much going on in this cloud. It's just kind of quiet, sitting there, not doing much of anything. This is a visible wavelength image of a patch of sky in the constellation Cassiopeia. We see a couple of cool things in here. There's a star that must be emitting a lot of ultraviolet light, and it's causing some gas around it to glow. That's why it has that red color. But in the rest of the frame, you see there's some dark streaks along the edges over here. And it's not because there are not stars there. The stars aren't missing. There's stuff in front of the stars blocking the light. So if we take an infrared image of the same area, we see a number of things popping up. First of all, there's a lot of dust that's glowing brightly in here. But all these very red stars suddenly pop into our field of view. Well, stars form in clouds of gas and dust. So these clouds, there's enough material there that gravity pulls that dust together and heats up and begins to form stars. And so these are the stars that I were talking about. These are the things that are, kind of 10,000 years old, sort of the baby stars. And we can't see them any other way than in the infrared because the dust absorbs them. And so with our infrared cameras, if we want to study how stars form, this is how we do it. We go into the infrared. You'll notice this little box over here that still has the visible wavelength image. If I put the infrared part in there, you see this big ring of gas and dust. There was a supernova there in 1572, Tycho's supernova, that blew out this shell of material, but the material is actually still very cold. So the only way we see it is at infrared wavelengths where we detect the heat from it. Now it's much colder than room temperature, but it's warm enough that we can see it. So in this image, we demonstrated those two features of the infrared that we like. We can see through dust, and we can also see very cold objects. So there's one more scientific technique I need to talk a little bit about, and that's spectroscopy, taking the spectrum of a source. So if you remember when we shone white light through the prism, we got that colored rainbow, so we got all the colors from the white light. If I take a tube of hydrogen gas and pass an electric current through it, it turns the hydrogen into a plasma and it glows this kind of pinkish purplish color. Well, if I look at that tube through a prism, what I'll see is multiple images of the tube, but I only see very discrete colors. I don't see a full rainbow. Well, it turns out all atoms have this have a signature, a thumbprint. And so if I measure the wavelength of those lines, I always see these lines at these wavelengths. So if I look at something and I see a wavelength of 656 nanometers, I know right away that that came from hydrogen. The neat thing is, if I have hot gas, hot hydrogen, it glows at those specific colors. If I have a cold container of hydrogen and put it in front of a white light source, I see absorption, I see dark lines at exactly those same wavelengths. So whether I have hot hydrogen glowing on its own, or whether I have cold hydrogen that's absorbing background starlight, I know there's hydrogen there. I mentioned every element has its own fingerprint. So hydrogen is a very simple atom, one proton, one electron, and so it has a very simple set of lines that it emits. Helium has 2 protons, 2 neutrons, 2 electrons. It's a bit more complex. As we get heavier and heavier, we get more lines and more complexity, but they are all a very unique fingerprint. So if I look at a star and I take its spectrum, I can figure out what's there just by looking for all these fingerprints. And in fact, if I take a spectrum of the sun, this is what it looks like. Normally if you you shouldn't look at the sun, but if you do look at the sun, it's kind of whitish, yellowish. You don't see anything particularly funny. But if you look at it through a high resolution spectrograph, this is what you see. And there's a big notch over in the red wavelengths. I said, aha, hydrogen has an absorption line at red wavelengths, so I know the sun has hydrogen in it. And in fact, people that do this for a living say there are 69 elements that we've discovered in sunlight. Hydrogen accounts for 92.1% of the atoms in the sun, helium for 7.8%, and everything else, those other 67 elements, form less than 0.1% of the sun's surface. But we know it's there, mostly hydrogen, a little bit of helium, and that's a common refrain whenever we look at stars. Another thing that spectra tell us is they can tell us how fast an object is moving. You've all heard a siren coming toward you. The pitch of the siren sounds higher than when it's stationary right next to you, and if it goes whizzing past you, the pitch is lower. It's the Doppler shift. Well, light does exactly the same thing. And so if I have my laboratory spectrum, sitting right in front of me, and I compare it to the spectrum of a star, the lines are pretty much the same place. This drawing exaggerates it a little bit, but in general, stars are at rest compared with us in the grand scheme of things, and so the wavelengths are all the same. But for galaxies that are nearby, and then some that are not so nearby, they're all receding from us because the universe is expanding. And so the wavelength of those lines shifts toward the red. And so we call this the redshift. So this galaxy actually isn't that far away. We'd say that that had a redshift of about 1/3, 0.3. That galaxy I showed you at the very beginning, that fuzzy little blob, has a redshift of 11, which means that the wavelength of light has been shifted a factor of 12 from what it would be in the laboratory. So that means that visible light from that galaxy has now been shifted way into the mid-infrared, just where my Miri instrument works. And so if we want to see galaxies near the fringe of the universe, we have to look in the infrared to see the light that we're used to seeing in nearby galaxies. Okay, just a quick side note, as pretty as the rainbows are, they really aren't very useful in terms of analyzing things. So we plot the brightness of the spectrum as a function of wavelengths, so you always see plots. And so where there's a bright line, that's a spike on this spectrum, and if there were a spike downward, that would tell you there's an absorption line there. That's important because when we work in the infrared, we don't get rainbows because our eyes don't see that. This is a very young star. This is one of these baby stars that I'm interested in. And baby stars tend to be very messy, just like human babies. They tend to burp up bubbles of stuff and throw things around. But we'd like to get a spectrum of this thing just to understand what kind of material is there. If we do, this is an infrared spectrum. I should have said that at visible wavelengths, we see mostly atoms. At infrared wavelengths, we see mostly molecules. They're larger, they tend to have lower energy states that we're looking at. So this is a spectrum of that baby star. There's a big absorption feature here that's labeled silicates. Silicates are a type of rock. If you go down to Santa Monica Beach, you're surrounded by silicates. Sand grains are a form of silicates. There are also things like water ice, a little bit of carbon dioxide ice, and there's even a little bit of methane gas here. Now, being a good scientist, I employ my prodigious powers of scientific reasoning and come to the very firm conclusion that there are cows in space. Okay, this is a joke. I don't want this to show up in the tabloids tomorrow. A top NASA scientist did not announce the discovery of cows in space. But it's important because these are the molecules that are important for life on Earth. And so it's good, maybe reassuring, that the molecules that we depend on here are actually relatively common in space. And so it helps us understand how our solar system formed, when stars form, they form out of the same stuff that we find on Earth that drives life here. Another thing that we can learn from infrared light is, as we start studying planets around nearby stars, we'd like to study their atmospheres and whether they're rocky or whether they're like Earth or whether they're gaseous like Jupiter. So if we know that we've got a star and a planet, with a planet orbiting the star, we can't separate them. So we can't take an image, usually we can't take an image of here's the star, here's the planet. Generally, we only see the light from both of them together. But if we know that a planet crosses in front of a star transit, maybe you've heard about the Venus transit a couple of years back where Venus passed in front of the face of the sun. When a planet passes in front of the star, it blocks some of the light, and so the apparent intensity of the star drops a little bit. But then there's a phase where we see both of them together before the planet hides behind the star at the other end. But this part is interesting, because if there's a big difference in temperature of the planet between the daytime side of the planet and the nighttime side of the planet, we'll actually see a little bit more infrared or a little bit less infrared, depending on where the planet is in its orbit. So if we're seeing the backside nighttime side of the planet, there's a little less light. As it swings around to the day side, from our view, it's actually a little brighter. So the fact that the light from the planet and star rose a little bit as we went to the daytime side tells us that there's a pretty good temperature difference between the day side and the night side of this planet. And so it probably doesn't have a really thick atmosphere like Venus. It's something a little bit more transparent, maybe like ours. So that's exciting. Hey, we found out a little bit about this other planet. We've been able to do a little bit with atmospheres of planets. This is a model spectrum of an atmosphere. And this is what the Spitzer Space Telescope was able to observe. It was only able to look at this in 3 different colors. And they noticed that it was a little bit dimmer at 3.8 microns than they thought it should be, and a little bit brighter out here at 6 microns. And so they fit that atmospheric model and said, yeah, this might be able to work. One of the things that the Webb telescope will do, it will actually let us get this spectrum, and so maybe we'll actually see that curve and confirm that the atmosphere really worked that way. So if the infrared is so neat, and I hope I convinced you that it is, it's really a lot of fun to play with, why doesn't everybody in the world and their dog have an infrared telescope in their backyard? Well, there are three things that make this a difficult place to have your career. First is room temperature emission, and I'll explain what I mean. Second thing is the atmosphere, and I'll explain what that means. And then third, just the sensors that we use for infrared astronomy can cause a fair amount of trouble on their own. Any object that's at a finite temperature emits radiation with a very characteristic spectrum, and we call this a black body spectrum. Stars that are extremely hot, 10,000 to 100,000 degrees, actually emit most of their light in ultraviolet wavelengths. More normal stars like the sun emit most of their light at visible wavelengths, which makes sense because that's what our eyes see, and so it makes sense for our eyes to have adapted to what our star puts out. So that's why we have visible wavelengths, and that's where the sun emits. Those clouds of gas and dust that I mentioned where we form stars, they tend to be very cold, 15 to 30 degrees above absolute zero. So they actually emit most of their light, their radiation at the very long far infrared wavelengths. And then the cosmic microwave background, which is a little bit under 3 degrees above absolute zero, emits in the millimeter. That leaves this nice curve in the middle. That red curve is in the mid-infrared. Its wavelengths around 10 microns, exactly where my instrument works. And that's where the Earth emits, and where the atmosphere emits, and where astronomers emit. Everything in the mid-infrared is glowing. One of the infrared astronomers quoted, "Observing in the infrared is like observing in broad daylight with a telescope made out of light bulbs." Where do the stars go during the day? They're still there, right? Stars don't move compared to us very much, so they're still there, but we can't see them because the Earth's atmosphere scatters blue light from the sun, and the glow of that scattered light just washes out our ability to see stars. If you got a telescope out in the middle of the day, you actually could see a few stars, but it's really hard because the sky is so bright. Well, that's what it is like all the time in the mid-infrared. So when I said I built instruments that went on Keck and on Palomar, we were fighting the atmospheric glow. It didn't matter if we were observing daytime or nighttime, it's always bad. So that's one reason why we want to put things in space. Second is our Earth's atmosphere isn't very cooperative. That same atmosphere that makes it possible for us to be alive also likes to make it difficult for infrared astronomers. At visible wavelengths in this range, most of the light gets through the atmosphere down to the ground, and so that's why big telescopes on the ground work. But there are certain wavelengths where molecules in our atmosphere absorb all the light, and so the atmosphere is actually opaque at those wavelengths. A lot of it's just from water vapor, some of it's carbon dioxide. There's even a little bit of absorption from ozone in our atmosphere. Well, the weathermen love this because they build satellites that observe at 6 microns. And if you've ever gone to NOAA website or Wonderground or whatever, you might have seen water vapor maps that tell us where the storms are, where all the water moisture is. So there's a big band of moisture blowing up through northern Mexico and Texas. Southern California is a little drier. There's a big band out over the ocean just north of the Hawaiian Islands where there's very little water vapor, and so you see all the way down to the surface of the Earth. That's why it's so dark. So weathermen like it, astronomers on the ground, not so much. And then finally, the sensors themselves. It sounds a little funny, but if you have a sensor that's sensitive to temperature, the sensor has to be colder than the stuff it's trying to detect, otherwise it detects itself. So we have to cool things in the infrared to very cold temperatures, and if you do that in the air freezes on your detectors and that messes everything up. There are also some false signals that are generated by the detectors, and so we have to get them even colder. Most of the 3 of the instruments on James Webb need to be cooled to 40 degrees above absolute zero to work. Miri, the instrument I work on, needs to be cooled to about 6 degrees above absolute zero in order to work. So all those things together, the radiation of room temperature things, the atmosphere, and just our sensors, really does mean we want to put our infrared telescopes up in space so we can see what's going on. So to address the scientific questions, to make things work in the infrared, we're building the Webb telescope. So Webb is a 6-meter infrared optimized telescope. You'll notice the primary mirror is coated with gold rather than silver. Gold is actually a better reflector of infrared wavelengths than silver is. It has 4 instruments that cover 0.7 to 28 microns. Now, I know that doesn't mean much, but the reddest color your eyes can see is right about 0.7 microns. So James Webb takes off right where your vision fails, so into the infrared past that. Webb is a partnership between NASA, the European Space Agency, and the Canadian Space Agency. None of us can go it alone. We got to work together on this stuff. And it's going to be launched on a European Ariane 5 rocket. Now, you saw the picture of Webb sitting in the clean room at Goddard, all unfolded. That does not fit in any rocket currently in production. We've got to fold it up. And so you'll notice that 3 of the mirror panels on this side and 3 on the other side fold back. That secondary mirror that's supposed to be out here is up on top. The sunshade is folded up like, kind of like butterfly wings tucked in there. And so James Webb Space Telescope is an origami telescope. It's got to unfold. After it launches, the fairing separates, things begin to expand. So first we got to get our solar panels out so we can get power. There's a lock on the antenna. We pitch the telescope a little bit and we do some course corrections. A long course correction, apparently. Pitch back a little bit. We extend our antenna so we can establish high-speed communications with the Earth. It's all low speed up to that point. Another little course correction. Then we begin to unfold stuff. So first we're going to start with that sun shield. So first the structures that actually hold the sun shield fold back from the telescope. We do the front side first. Then the back side comes down. Now, to help the telescope clear that sun shield, the telescope itself is actually on a tower that separates it from the rest of the spacecraft, and that tower has to extend about 6 feet in order that nothing in that sunshade touches the telescope. So that was that tower deployment. The covers come off the top of the sun shield. This is all packaged like some little tinfoil wrapping thing. We release a couple of locks, and then these booms deploy that stretch out that sun shield from where it's folded up in the center. So we do one side first, then the other side. Now that sun shield is actually 5 layers of material. And it's very important that those 5 layers separate because on the sun side, the temperature of this first layer is about room temperature, about 300 degrees above absolute zero. But the telescope needs to be 50 degrees above absolute zero, so this top shade has to be 50. So if there's any touching in between, it will heat up the next layer and we won't get cold enough. So that's one of our big concerns. Now we're getting ready to release the secondary mirror. And so you can see the structure starting to move. Then the secondary mirror, which is here, swings forward and moves to the front of the primary mirror. And then finally, the side wings of the telescope primary mirror move into position. Here comes the other side. That whole process takes 2 weeks. So the Mars guys had 7 minutes of terror while they were trying to land a rover on Mars. We got 2 weeks of terror waiting for our telescope to deploy. After it's fully unfolded, then begins the long process that the whole telescope has to cool down. Our instruments have to cool down. Until everything is settled, we've made sure everything works. We do our calibrations. It's 6 months after launch before we're ready to start taking scientific data. So it's a long one. Another thing different between Webb and Hubble is where it's located in space. Hubble actually orbits the Earth just a few hundred miles up, so it actually orbits the Earth every 90 minutes. And some evenings when Hubble goes overhead, you can watch it streak across the sky. Webb is going to be located 1 million miles from Earth, 4 times the distance of the Moon. There are 5 spots between the Earth and the Sun where the gravity of the Earth and Sun balance the tendency of the spacecraft to go running off on its own. These are called Lagrange points, after the mathematician who discovered them. The second Lagrange point, nicknamed L2, is actually a really nice place to put spacecraft because our sun shield will always shield the Earth, the Moon, and the Sun from shining on the telescope. We've sent a number of spacecraft out there. Webb will be joining the collection. So I mentioned Webb has 4 instruments, so I'd like to describe them very quickly. NIRCam is our near-infrared camera. It's primarily to take pictures of things. It has a tool called a coronagraph, which I'll explain in a second, and it does some very simple spectroscopy. So the top is some images from the Hubble Space Telescope with the wide field camera number 3, which has limited infrared capabilities. If we were to image the same galaxy with Webb, not only do we see fainter galaxies around it because we have so much more collecting area, but we begin to see some of the spots that are just sort of fuzzy in the Hubble image. And again, this is a simulation. We don't have anything yet. But these spots, might be regions where stars are being actively formed, or they might be remnants of those little galaxies that collided, that merged together to form a larger galaxy. But that's the kind of stuff we want to find out with Webb. And so it'll be a great tool for examining these very early galaxies. A coronagraph is an instrument that blocks the starlight. So whatever's right in the center of the coronagraph, the light from that gets blocked. So we'll put a star right in the center. And so where the star was gets blocked out, so we don't see the starlight at all. But that allows us to see other structures around the star that normally are lost in the glare. The star is so bright that we can't see these things. This is a star called Beta Pictoris, and we saw this kind of disk structure. And we said, in our solar system, we have a similar sort of thing. We have zodiacal light, which is dust near the Earth that on a good dark night out in the desert, you might be able to see as a band of light. Well, this is much thicker than in our own solar system, but we said, hey, that's kind of a signature of a solar system. Wonder if there are planets in there. Well, a few years later, after our coronagraphs improved, we have a coronagraph which is much tighter, and we noticed there was a spot next to that star. And it turned out they imaged it again 6 months later, and that spot was on the other side of the star. Turns out this is a planet. So it has, I don't remember what the period is, some number of years. But we saw it in part of its orbit, and it'll go around for quite a while before it gets all the way around. But with these coronagraphs, we can actually take direct images of planets. So if the planet is far enough from the star, we might be able to detect it. And so that's something that people are very, very eager to do with the Webb telescope. NIRSpec is our big spectrometer. A couple interesting things about it. It has 2 ways of making a spectrum. It uses microshutters, and it has an integral field unit, which are really technical terms, but I'll explain what they mean. With a microshutter, it's like shutters that you put on your windows. You have all the slats, and you can open some of the slats, if it's maybe broken, to let in light from one slat and not the others. So if we have an image of galaxies on the sky, we can put the microshutter array in front of them, and then we can choose which shutters to open so that we get spectra of just the galaxies that we're interested in. So here we've opened a few shutters, and maybe that one corresponds to that galaxy, this one to that one, and that to that. I don't know. The drawing wasn't very good. But the point is we can get spectra of those 3 galaxies at exactly the same time. In fact, we can do up to 100 at one time, which when you have a big, expensive telescope, it's good to do as many things at the same time as you can. So this is one way to get information on many different objects. So that's what we call the microshutter array with the spectrometer. The other thing, the integral field unit takes a tiny square of sky and slices it up. So it uses a special mirror that has these steps on it so that the top slice gets put into the spectrometer on the left edge, the next slice next to it, and so forth. So we spread these 6 slices out and get the spectra simultaneously. And so it's another way to get information over a larger area all at one time. One of the neat things you can do with this is if you put such an integral field unit on a galaxy, remember I talked about red shifts and blue shifts? You can see those Doppler shifts in the stars in the galaxy. And so we can actually tell which way the galaxy is rotating. This top galaxy, the lower end is coming toward us, it's blue shifted. The top end is moving away from us from the red shift. This galaxy is sort of the same thing. So in both of these galaxies, we see strong signatures of rotation. We can tell how fast it's rotating, which tells us how big the galaxy is. And so it's an important tool for understanding those galaxies, at the far fringes, understanding how they formed. The fine guidance sensor near us is actually sort of two instruments in one. I should have said NIRCam was built by the University of Arizona, and NIRSpec was built by the European Space Agency. FGS NIRIS is built by the Canadian Space Agency. It serves as the fine guidance sensor to help us actually point the telescope and lock onto stars. The near-infrared imager and slitless spectrograph is sort of a specialized imager and spectrograph. It doesn't duplicate what the other 2 infrared instruments do. One of the neat things that it does do is it has the ability to take spectra of the same fields in 2 different directions. So there's a pair of stars here, and in this image, the starlight is spread horizontally. The same 2 stars are over here, and this way the light is spread vertically. What's the big deal? Well, if you're getting spectra of all these objects at the same time, it's inevitable that 2 stars, the spectra overlap each other one direction, but when I get to spectra in the other direction, they're well separated. And so one image or the other will give me a good spectrum of the sources that I'm interested in. Okay, finally, the 4th instrument, this is Miri. This is the instrument that we've been working on here at JPL. The other 3 instruments all work from about 1 to 5 microns. Miri works 5 to 28 microns. Because we're the only instrument that works at these wavelengths, we have to do all the things that the other instruments do. So we have an imaging capability, we have chronographs, and we have a spectrometer. I forgot to point out, at JPL, we were responsible for the detectors. And every image of Miri that I can find on the web, they always hide my detectors. So gratuitous self-promotion. This is what one of the JPL lead detectors actually looks like. Yes, that's me. You can tell by the eyebrows. This is Kalyani Sukatmi, who was, until recently, our project manager. So this was early on when we first delivered the detectors to be bolted onto the rest of the instrument. A few words on why we want a mid-infrared instrument in the first place. If we can learn a lot from the near-infrared instruments, why do we need a mid-infrared instrument? Near-infrared, we detect mostly the ultraviolet light from those galaxies that are very far away, that have been redshifted from ultraviolet to the near-infrared. Well, the visible light from those galaxies gets redshifted into the mid-infrared. So if we want to study the normal stars in those really far away galaxies, we need to look at them in the mid-infrared. We see mostly atoms and molecules in high energy conditions, high temperatures in the near-infrared. We see molecules in lower energy conditions in the mid-infrared. If we look at stars that are forming planets, we see the more mature stars in the mid-infrared. If you want to see the very young stars that are still themselves in the process of forming, we see that in the mid-infrared. And finally, if you're looking at the planets themselves in the near-infrared, we tend to see the really hot stars that are close, or really hot planets that are close to the stars, things that are 1,000 degrees, someplace we definitely don't want to visit. If you want to study planets that are more room temperature, more like the Earth, then we'll want to look at those in the mid-infrared. And there are many, many more reasons, but these are a few of the things that are important. A little bit more about Miri. All the other instruments were built, or at least there was one organization responsible for the instrument. With Miri, it was a 50-50 partnership from the beginning. JPL, it was responsible for half the instrument. the detectors, the electronics to run the detectors, and the cooler that gets us down to that 6 Kelvin temperature were all the responsibility of JPL. 24 astronomical institutes in 10 different European countries were responsible for the optics and the structure of the instrument. And when this was first proposed to our senior management here at JPL, they all shook their head and said, it's never going to work. I'm pleased to say it worked actually very, very well. We had great people on both sides of the pond, so to speak, and I think we have a really great instrument. What do I want to look at myself? In the introduction, Mark explained that I'm interested in star formation. I do have a little bit of time of my own on Webb where I can point it at anything I please. And so what do I want to look at? Well, I got some questions. I'd like to understand how binary stars form. About half the stars that you see in the nighttime sky are actually binaries, two stars that are orbiting each other. When we look at very young stars, the stars that are still in the process of forming, it's more like 80 to 90% of them. So why do stars form as binaries and then lose their companions along the way? So I'd like to understand a little bit more about those binaries. Also, I mentioned that planetary nebulae with that kind of wing, that low wing-shaped structure, generally need binary stars to form structures like that. So the common theme is binary stars. So I'd like to know a little bit more about what shapes the planetary nebulae. This is a very young star. It's actually a triple system. So there are 3 stars here. The bluish color of these 2 stars generally indicate that they are hotter. They might even be almost normal stars. Whereas this yellow-reddish color, because this is a mid-infrared image, this we would normally interpret as a very young star. Well, if they're gravitationally bound to each other, they had to have formed at the same time. So how is it that you can have 2 older-looking stars and a younger-looking star? If you get crude spectra of these stars, the 2 top sources are the white and red curves up here. They're kind of normal and flat. This is relative to a normal star spectrum. So they look about normal. But this yellowish star has much more infrared radiation than getting toward the visible. So it's much colder in apparent temperature. But the important thing is that the solid lines were data that was taken at one period of time, and then the dashed lines was 3 years later. So these 2 stars stayed roughly constant. But this star actually, not only did it get brighter at short wavelengths, the temperature actually got apparently hotter. So what's going on? So one of the ideas is that gas and dust that forms the stars is still streaming onto that star, and as it falls onto the star, it heats up and causes the changes in temperatures and so forth. So with Webb, I'd like to study that a little bit more. I should be able to see material actually around the star, perhaps flowing into that star. On the planetary nebula side, this is a different planetary nebula called the Egg Nebula. The image on the right was taken with Hubble. And so it shows these neat lobes that are blowing out from a star that you actually can't see. There's a big disk of dust around the center that's absorbing all the starlight in the center. This image was data that I took with the Keck telescope with my mid-infrared camera on the ground, where it's really hard to see stuff. But even so, you can trace the lobes of that planetary right down to the center. We still don't quite see the central star. That's just a blob of dust. That's not the star itself. But it's hard to see here, but there's also sort of a halo around it where that warm dust in the disk is glowing, emitting its own light. This is another planetary nebula. This one looks a little normal. It's kind of round, and it's a little bubbly in the center, but it's fairly unremarkable. But when we looked at this planetary nebula with the WISE All-Sky Survey, we discovered that it had a pair of concentric rings around it. So how did that structure form? This also requires a binary star to shape it. And so we're still trying to understand just how does that work? What makes those shapes? And so I'd like to use Webb to get information about those rings, what they're composed of, what the energy situation is like, to see if we can understand a little bit better what's going on with that planetary nebula. Okay, what's Webb's status and what's up next? So Miri was the first instrument delivered. It was installed into the Science Instrument Module in 2013. And I do have to point out the detectors are on the back side, and so you can't see them again. All the instruments were on board by 2014, within the year after that. And then it went through a number of rounds of testing. We wanted to make sure that the instruments all made it to the Goddard Space Flight Center in one piece. We wanted to make sure that the computers that are going to run the Science Instrument Module were actually able to control the instruments. And they went through a number of tests to make sure they'd survive launch and all that sort of stuff. Just earlier this year, you may have seen some of these pictures. The telescope itself was completed. And then just a few months ago, that instrument module in the previous picture was lowered onto the backside of the telescope, so it was installed behind the primary mirror. And so that whole assembly is now ready to go through its own testing. Its next stop is actually the Johnson Space Flight Center down in Houston, where it will go into Chamber A. This is a huge vacuum chamber that was used during the Apollo missions, where they'd test the Apollo spacecraft. And in fact, they would throw people inside there, the astronauts, because they needed to train to work in a vacuum environment. So it's been repurposed to test the Webb telescope. This is what the telescope will look like inside the chamber. And then there are a bunch of light sources and other instruments up on the top to measure the properties of the optics of the telescope to make sure they're what they're supposed to be. We can't refurbish Webb, so it has to work the first time. So after the testing at Johnson, the telescope will make its way to Northrop Grumman, right down here in Redondo Beach. The spacecraft, that propulsion system and all that stuff, and the sun shield will be bolted together. The telescope will then be connected with it, and we'll have a completed observatory. In early 2018, there'll be some short, it's probably still a couple of months, but a short functional test to make sure everything is ready to go. And then in October 2018, hopefully, we launch. And with any luck, you'll invite me back in about 3 years to give you a few of the first results. So that's it. I hope you learned a little bit, and I'd be happy to take questions. So if you do have questions, please come up to the microphone.
Did you say when Webb goes operational, Hubble will still be in operation?
We hope so. The only thing really limiting it is whether any of the gyroscopes in Hubble break and whether there's enough funding to actually operate both of them at the same time. But we think we'll get at least a year or two of overlap, at least fingers crossed. Yes?
Thanks for a great talk. I was interested in learning more about the 6 Kelvin requirement for Miri.
Yes.
And how you plan to achieve the 6 Kelvin requirement and how long it has to be at that 6 Kelvin temperature range when you're taking measurements?
Okay, so all the other instruments operate at about 40 Kelvin, and we can get to that temperature just based on cooling of space. We call it radiative cooling. Miri, to get down to 6 Kelvin, actually requires a cooler, a cryocooler. Comparing it to your refrigerator in your house isn't really fair, but it's kind of like the refrigerator or freezer in your house. It is a mechanical cooler, so it should last for a very, very long time. In fact, we think the final limit to the lifetime of Webb is actually the propulsion, our ability to steer. If nothing breaks, if everything survives launch, everything should be able to go at least 10 years. That's the goal. 5 years for sure. Hopefully 10 years, maybe longer. But it is a mechanical cooler that gets us to 6 Kelvin.
Thank you.
Right?
Hi. Had
Hi.
a couple of questions. First one, I'll just rattle out the questions. You can pick them in order. First one is, what's the difference between a slitted spectrograph and a slitless spectrograph?
Okay.
Second question, is there any plans for using a star shield or solar shield in conjunction for a chronograph? Third, I noticed some
I have to remember all of these.
some flags at the back end, or the aft end of the instrument. Can you tell us a little bit about station keeping and what's involved with that?
Okay, so let's see. First question.
Slit and slitless.
Slitless and slitted, okay. So normally we want to limit the light that enters the spectrograph. And so we use a small slit so that it isolates the galaxy or star that we're looking at. What it does is eliminates all the background from the rest of the field of view. And so it lets us concentrate on that one object. In a slitless spectrograph, we still use the prism or grating or whatever the spectrograph uses, but now we don't isolate it. So we get light from every point in the sky that enters the instrument. So what happens is with a slitted spectrograph, you'll have 1 micron light here, 5 micron light there, and you know exactly where everything is. With slitless, one star's 1 micron light be here, but another star's 1 micron light might be over here. And so you have a mixture of things, and so it's not as sensitive, but if you have a lot of bright objects, it lets you get crude spectra of many things all at once. So there are advantages to both. Most of the time we use some version of a slit spectrograph, but occasionally we don't care so much, we just want to look at something really bright, and then we'll use the slitless. Little crazy, but it's all good stuff. Okay, you're going to have to do it again.
Second question was if there was any plans for
the star shape.
non-collocated, non-circular coronagraph.
So there are studies of whether you could fly something in front of James Webb at some point in the future. There are studies. It's probably not going to work with Webb itself. The timing just isn't right. They'll probably need a dedicated mission to do something like that. It's a neat concept, and it will happen someday, but I don't think the Webb is quite the right time to do that. And then the third one was?
Station keeping. There was
station
some
keeping, yeah. Okay, so
flags.
in that little video, you saw some momentum flaps on the back. So it's a somewhat standard system. It uses reaction wheels. It uses those momentum flaps to help move things around. When it needs to do a small course correction to keep it in that orbit around L2, then it does use a little bit of propellant. So it's sort of a mixture of all of them to make sure it's pointing where we want it to point. Okay?
Thank you.
So I had a very fundamental question about the early galaxies. So how do we actually see them, right? Because everything started with the Big Bang and went away from it. So how is that light not already how do we actually see them, right? How is that light not past us since we don't travel faster than light?
The universe is kind of a big time machine. It takes a certain amount of time for light from that galaxy to get to us. So, those galaxies that we see 13.4 billion light years away, that light left that long ago. So we only see the galaxy at that age. We have no idea what it looks like now. So, as the universe is expanding, that light is redshifted, and that's why we see it in the infrared. But, we really are seeing it a long time ago. So it's, I don't know if I answered that very well, but, we are seeing the light that traveled a long time to get to us.
Okay, so it lasted long enough for us to essentially travel all that distance and then kept emitting.
Right,
okay.
So that light's catching up to us as that galaxy is receding away from us. Okay?
My question is two parts, but it's basically about the sun shield.
Yep.
So is it true that this really huge sun shield allows you to do the cooling without having like liquid hydrogen or liquid helium or something, and so therefore you won't run out like you did with Spitzer?
Right, that's right. So the sun shield provides an environment where the telescope and 3 of the 4 instruments can cool to 40 to 50 Kelvin on their own. There are some other radiators that are kind of tacked around the back to help with that process. But yeah, that sun shield has to work exactly the way it's supposed to in order to give us that environment.
So that's a more ambitious sun shield than you ever had before.
Yes, absolutely.
So then the next question, part of it is how much of a constraint is the sun shield as far as where you point the telescope? Obviously, you can't point it toward the sun.
Right.
Can you still see like half the space at one time?
Yeah. Unfortunately, I deleted that slide to save some time, but I have a slide on exactly that. So if you imagine a plane between the sun and the Earth, JWST can point essentially straight up or straight out, so there's kind of a ring that we can spin the telescope around. We can't point directly away from the sun because then that would slide the telescope around, into the field of view of the sun because the sunshade wouldn't block us anymore. So there's actually a band about 45 degrees wide, kind of ringed around the sky that we can observe at any given time.
But then you just wait until the Earth moves around to get the
So
rest of it.
if your object happens to be directly apart from the sun, you get to wait 4 or 5 months before you have a chance to look at it.
Thank you.
Welcome.
Well, I have two questions. The first is I'd love to hear about how James Webb will be used to study exoplanets, and in particular, will it be taking a look at the planet around Proxima Centauri? How will it help us learning more about their atmospheres of potential nearby Earth-like worlds? And my second question is, will JWST help with figuring out what makes up dark matter and dark energy?
So yes to both of the above. Exoplanets is actually a very hot topic right now, of course. Certain people think they ought to just take 25% of Webb time and devote it to exoplanets right off the top. The rest of us that don't care so much about exoplanets are going to fight that, but yeah, so
Don't.
exoplanets are a very big thing, of course. So I showed a couple of examples of things that we might be able to do studying exoplanets. They are very clever. They will come up with ways to observe these things. The problem, from my perspective, is we built a very exquisitely sensitive instrument that was designed to look at these galaxies 13.8 billion light years away. And they're going to point it at the 10 brightest stars in the sky. It drives me nuts. But it's great science. It needs to be done. It is going to be tricky because the stars are so bright. The instruments are going to have some problems dealing with all that. But we're studying ways to do the observations to make sure they can actually be done and that we can get the science that we're after. So that was the exoplanet question. And then dark matter. There are actually other missions coming along that will do a better job, but certainly there are aspects of dark matter studies that Webb will be able to do. Certainly, the gravitational lensing helps us understand the distribution of matter in the galaxy clusters that act as the lenses. So we can't see all of what that matter is, so some component of that has got to be the dark matter. But there are other missions that are being studied that will actually be able to let us look at a much broader part of the sky and look for the very tiny gravitational influences that will help map dark matter around the sky. So somewhat yes, but there are actually, it sounds a little funny, but there are somewhat better ways to do it. And so Webb is part of it, and then there'll be other things that do it as well.
And dark energy?
Now we're getting tricky. Actually, I think I'm going to have to say I don't know on this one. I know a little bit about the field, but not enough to know whether Webb can really help out. I mean, certainly it will be able to contribute to our understanding of the expansion and acceleration rate of the universe, but I haven't thought about it enough to know what we can really do. So I don't want to answer incorrectly.
Okay, thank you.
Yes?
Thanks for the presentation. I'm wondering what kind of redundancy is built into these sensors, seeing as L2 is a bit far for a repair mission?
Yeah. So that was a hot topic when we first started designing our instruments and the observatory. We want things redundant, so if something does fail, we can switch from the A side to the B side and let us continue. The sensors themselves are so hard to manufacture that almost all of them are not redundant, meaning that if the imaging, we have 3 detectors in Miri. There's 1 for the imager part and 2 for the spectrometer. If any one of those detectors fails, we actually lose our ability to do science with that capability. Now, the electronics that drives the detectors are redundant. We have an A and a B side, but because of constraints when we were doing the design, the sensors themselves are not. So I'm going to have 6 months of terror waiting to make sure that everything in the instrument is actually working really as well as it can. It's actually closer to 2.5 months, but until the instrument is cold enough where I can see all the detectors working properly. But yeah, that's absolutely a concern. That's part of why all our tests take so long. The tests that we did on the instrument module, each of the 3 tests was about 3 months long. We're doing all the testing to make sure that they will survive vibration, they'll survive cooling down, because we can't afford to have anything go wrong. So some redundancy, but maybe not as much as I'd like.
Thanks.
Okay.
How much of the cost of the Space Telescope is in the design and mission planning, and how much of it is in the manufacturing? Like, so if you have a launch failure, how difficult is it to spin back up and relaunch a similar mission?
Yes. No, that's actually a really great question, and it's good because people often see the price tag of the Webb telescope and say, holy cow, how expensive is that thing? Well, the cost numbers that you see actually cover all phases of the development and operation of Webb. So I can't give you exact numbers because I don't know them. Maybe the folks over at Goddard want to take a crack at that one. But there was money that went into the original concept studies, then money to do the designs, the construction. The cost numbers that you see actually include 5 years of operation, so they include launch and 5 years of operation after that. I mean, most of the money goes into the construction of the telescope, of course, but it does include from the first idea to the end of the mission. Okay? We have some online questions? Oh, go ahead.
I got one question. How long, I may have missed it, how long does it take actually to get from Earth to L2? 1 million miles.
So that actually takes most of those 2 weeks. There is a point where we actually go into orbit around the L2 point. It's not that we go to a point and park there. We actually do sort of a lazy 6-month orbit around that spot. It's somewhere between 2 weeks and a month before we actually get.
And what does it use for propulsion? Does it have a rocket on it when it's going there, or how does it?
Little thrusters. I'm not sure what the propellant actually is, but it's kind of typical thrusters that we use.
And the power source is just sunlight?
Solar panels. Big solar panels that are underneath that sun shield. Okay. So I got a couple online questions. Kieran asks, I've heard ozone in the Earth's atmosphere absorbs UV radiation. Does it also absorb infrared, but not visible light? I can't say whether it absorbs anything at visible wavelengths, but I had a slide way back that showed the absorption spectrum of Earth's atmosphere. And at 9.7 microns, there is a fairly strong ozone absorption band. So a telescope looking on the ground, pointing up, can actually see the absorption of ozone at those wavelengths. So yes, we definitely do see some in the infrared. What's that? Oh, no. Okay. Skara, hopefully I'm pronouncing that right. Skara asks, the ability to service Hubble saved and improved it. Worried about Webb. Please talk about how well it is built and alleviate my worries. Okay, so we talked a little bit about this with one of the previous questions with redundancy. So as many of the systems as possible, we do make redundant so that if one half fails, we switch over to the other half. And the other thing we do is we do a lot of what we call environmental testing. We took each of the instruments to a vibration table. We bolted onto these tables that then shake like crazy to simulate the launch of the rocket. After we delivered the instruments into that science instrument module, that whole science instrument module was shaken. Then when the science instrument module was bolted onto the telescope, it was shaken again. We keep shaking things like, hey guys, you're gonna break it. But we do these tests, not quite to launch levels, but we do these tests to make sure that things are properly mounted, that something's not gonna break loose and fail, and that the way we built the instruments and the telescope in the first place can survive all that. We've actually cooled the instruments down to their operating temperature. Well, the instruments themselves have been down to operating temperature at least a few times. And then as a science instrument package, that's also been cooled down to operating temperatures 3 times. So we do a number of these tests to try to make sure everything really is functioning the way it's supposed to and that it's robust, that we don't expect it to break. It is true we cannot service Webb. We really do have to get it to work the first time. But we learned a lot of things from Hubble, so hopefully we won't make the same mistakes twice. Hopefully we don't make too many new mistakes. But that's also part of why these things cost so much. We have to do a lot of testing to make sure that everything is going to make it to where it's supposed to be. So hopefully I've reassured you a little bit. I'm going to be holding my breath too and have every body part I can come up with crossed as well when we launch. So I know that's not perfect assurance, but we're doing our best to make sure it's all okay. Okay, any other questions? Yes.
Oh, question. I was wondering how is the hexagonal primary mirror of Webb is a better choice, so to say, than a round mirror of Hubble?
Okay, so because the mirror had the fold, that's why we use the hexagonal segments. The Keck telescopes in Hawaii actually have a similar design where they have hexagonal mirrors. They actually have 36 mirrors where we only have 18. On the back of each mirror is a system of actuators that moves each segment little bits to make sure that each segment lines up exactly where it's supposed to be and that the entire system works like one big mirror rather than 18 little mirrors. So it's that correction, that ability to position each mirror properly that allows it to work. So was there a little bit more to your question?
No, is the folding is the only reason why it has to be hexagonal? Or is there any other advantage to that?
Yeah, it's probably the biggest reason because it does have to fold. It's also easier to make lots of smaller mirrors, even if each mirror has to have its own specific shape. It's easier to make small mirrors than it is one gigantic mirror. The biggest single mirror telescopes on the ground are about 8 meters in diameter, so what's that, about 27 feet in diameter. The bigger ones, the 10-meter telescopes, like Keck, all use the hexagonal mirror structure. So manufacturing and the fact that we have to fold it up is what drove it. Okay?
Thank you.
Just curious, given that the mirror is exposed to space like it is as opposed to inside the tube in Hubble, how vulnerable is it to stuff, just random stuff? Yeah. I know there's less of it out at L2 than there is in Earth orbit, but still, is there any risk of that?
Yeah, we're going to get hit by stuff. That big sun shield is a great micrometeorite collector. So, we are worried about things zipping in and dinging the mirrors or plowing holes through the sun shield. So we have tried to model all those effects. So we have a beginning of life performance of the primary mirror, and then there's an end of life performance model where we try to take into account all those things. There will be damage over time. And so we think we know how well it will still work 5 years, 10 years on. And things are designed to deal with that as well as we can, but when you have an exposed mirror, you are going to get hit. It's just going to happen. And so you have to make sure that things are large enough, that you use materials that are good enough that you can control it somewhat, and that at the end of life, you'll still have really good performance. So yeah, absolutely, it is going to degrade with time. We just did our best to make sure it doesn't degrade faster than we think it's going to. The other thing we have to worry about when we launch it, it's going to be in Earth's atmosphere. It's going to carry some of that up with it. And so we'll have ice potentially freezing on things. And so we do have heaters to keep critical parts of the telescope and the instruments a little bit warmer than the not so critical stuff. So hopefully the ice freezes on the support struts and all the things that we don't care about and leave the optical surfaces relatively clean. So we do try to make sure we've caught all those things as we think about it. Okay?
So a lot of your sensors work at very cold temperatures, and you obviously test their function at those cold temperatures by cooling them down. How do you prevent any of those sensors from being damaged from the heat cycles, from the heating and cooling of the sensors?
So that's part of the qualification of the sensors. They have to be designed in a robust manner to make sure that they don't fracture when they cool. So I know the sensors in Miri the best, obviously. So the circuit board that our sensors are attached to were specifically chosen to contract and expand at the same rate that the sensors themselves expand and contract. So we don't want the thing that's holding the detector to crush it because it contracted faster than the detector did. And so we do those material analyses all through the design process to make sure that we're not going to do anything to crack them. And then the detector vendors that we contracted with to actually develop them, they have their own processes for making sure that the sensors can survive in the first place. And sometimes it takes a few years to get it right. But what we use flight-like detectors, so things that we don't intend to fly, but that were built at the same time. And we actually torture test those things. So one of the Miri sensors, we put through 100 thermal cycles going down to 6 Kelvin, back up to room temperature. Well, we cheated a little bit. We only went to 77 Kelvin and then back up to room temperature. If it can survive that, it'll survive 6 Kelvin. So we made sure it could go many, many, many cycles without anything happening. And that gives us confidence that only cooling it 5 or 6 times will be just fine. So it is something we study with those flight-like parts to make sure that there are no issues with it being cooled.
Thank you.
Okay?
Thank you for the lecture. Given the cost of the telescope itself and assuming that everything is work just fine, do you have any plan when it's done its mission? Like after 5 years, after 10 years? What you plan to do? Because for the cost, it's cost a lot of money. Do you plan to have something like repair it back to Earth, or are you just going to leave it in space?
So at this point, the plan is just leave it there. Eventually it will run out of propellant, and then it will start to drift away from L2, and it will just go into orbit around the sun. So it's not going to be a hazard to anything else. But as I say, hopefully it is the propellant that eventually stops us working. We hope maybe we can get 15 years out of it, maybe even a little more, depending on how frugal we are with the propellant. But eventually, it's just going to go away.
All right, thank you.
Yeah. Hey.
Had 2 more questions.
Okay.
First one's an easy one. If you could talk a little bit about the mechanics of the deployment. So obviously it's a pretty complex sequence of events.
Right.
Second question has to do with mirror segment geometry. It makes sense, obviously, to have hexagonal tiles in the interstitial portion, but on the outer point, are there any diffraction artifacts in band, and what would be the reason for leaving all the hexagonal edges as opposed to making a giant disk out of it at the periphery?
Right. Okay, so complexity of the mechanisms. All I can really say, because I'm not involved in the mechanical design of the telescope, early on, the scientific working group asked Northrop Grumman whether this was the most complex thing they've ever built. And the answer was no, it's the 4th most complex thing they've ever built, but we can't tell you about the other 3. So I'm trusting they know what they're doing. Then in terms of the mirror segments, yes, that actually is very much of an issue. If you look at the diffraction pattern, what a star looks like in JWST, it's not a nice round thing. It does have kind of ripples and stuff that follow that hexagonal overall structure. It's not bad enough to be a real issue. Our images will still look really pretty. We'll still be able to do really good science. They might have been able to round the edges to give it a more traditional round shape, but that's a lot of extra manufacturing cost that just wasn't worth it in the end. Each of the instruments, as we focus the starlight, there's actually a point in the optics where the telescope mirror itself comes into focus. So the stars are out of focus, but the telescope mirror is in focus. We call that a pupil. We actually put metal barriers at that pupil to make sure that no light is sneaking around through those gaps those rough edges so that we block out any stray starlight that might be trying to sneak around those cutouts. So the instruments were all designed with that shape in mind to do the best they can with it. And even our coronagraphs have some really interesting shaped pupil masks to try to block out any scattered light that might be associated with that. So yeah, it'd be nice if it was really round, but we can design our instruments to take it into account as best we can.
Thank you.
Okay. Yes?
Hi. I feel like you might have just mentioned that you can't answer my question, but I was wondering if you could talk a little more about the actual materials of like the structure of the telescope, or yeah, of the telescope, and like how much it weighs,
Yeah.
and if that was taken into consideration and like what the goal was.
I did not look up how much JWST weighs. I should have done it because that's a really good question. It's lighter than a lot of conventional telescopes because we do have to launch it. We have to put it in a rocket. For example, the mirrors are actually made of beryllium. It's a very lightweight metal. It's really nasty stuff to work with, but it's strong. It's relatively easy to shape, and it's been used in other space telescopes, so we know it's a good material. It's a robust material. And then that beryllium surface is coated with the gold. So the gold coating that you see is supported by beryllium mirrors. A lot of the support structure, some of the support structures at least, are carbon fiber composite materials, which are very lightweight and very thermally insulating. A lot of it's just aluminum. So, you know, they took every opportunity they could to lightweight things, but make sure that things are still strong enough that they'll survive the launch. So hopefully that's at least a partial answer to your question. Okay. Yes.
Hi. I was wondering, so if the Hubble telescope, this is going back to a gentleman's previous question, but if the Hubble telescope has a shroud to protect the mirror, what was the reasoning behind the JWST not having a shroud? Was it because that you couldn't like keep it to a cold enough temperature, or just the complexity of having something be able to extend that far since it's such a like wide diameter? Or why would they, because if it causes damage later?
Yeah, it's just structurally very challenging, and anything that would be light enough to actually be a light shield is going to take all those micrometeorites and stuff anyway. So it just wasn't practical with something this size, particularly because it had to fold up to have any kind of structure around it. So micrometeorites are going so fast, I'm not sure a Hubble-like shield would stop a lot of them anyway. I don't know how many have actually hit Hubble, but since it's low Earth orbit, it's a bit more shielded than we're going to be out at L2. But I think it's mostly just a matter of practicality. There's just no easy way to build a structure like that would do the job. And so, you know, we're relying on good baffling inside the telescope to block out that stray light.
Okay, thanks.
Okay. Hi.
How many steps does it take to make the full deployment?
Oh boy. There are, so the question, in case you didn't catch it, how many steps are there to do the full deployment? I'm actually not sure. It's got to be in the hundreds because you see all those little things unfolding. There are mechanisms all over the place. You know, there are 5 layers of sun shield. I don't know the right number, unfortunately, but there are a lot. That's why it looks so complex in that video with everything popping out. You know, it's like a transformer robot or something building the final telescope. So yes, there are definitely many, but I don't know the exact number.
When Hubble was brought online, it was found to be nearsighted. That's not happening, right?
So this is why I specifically mentioned that we learned our lessons. We have a test that was just completed just a few days ago was to actually measure the curvature of the primary mirror to make sure that the curvature was the right shape, right dimensions, and all that. So, you know, we are doing the tests to make sure our optics are what they're supposed to be. We are double checking, so we're not throwing out one result that doesn't quite agree with everything else. it's still an observatory designed by human beings, and occasionally we miss stuff. So we're doing our best to make sure we don't miss anything. You know, again, this has to work the first time. But, you know, we did learn lessons, and so we have procedures in place that are designed to catch mistakes like that. Humans are inventive. I'm sure we'll come up with new mistakes to make, but at least for the things that we know about, we're doing our best to make sure that we don't make that mistake again. Yes?
Since the propellant's the first thing to possibly go, hopefully, is there room for possibly sending a refuel mission?
So even though we have no current way of servicing the Webb telescope, it was decreed that there would at least be kind of a grappling hook or some sort of attachment point that a future rocket could attach itself to. I don't think there's any way to do a refuel, even if you did get a spacecraft there. You know, I don't know where the propellant tanks are. I'm guessing they're fairly buried. But this is mostly conjecture on my part, so don't take what I say as fact, but I don't believe there's any way to actually do it, even though we've all had that same idea. Okay, thanks for coming. Great questions. Have a great night.